Ladies and gentlemen, finally we will listen the final plenary by Professor Mulyana talking about clean energy devices for sustainable future, and Dr. Munawar Halil as the moderator in a panel. We would like to invite Professor Mulyana and Dr. Munawar Halil to the stage.
Very good morning, everyone. Ladies and gentlemen, welcome to our third plenary sessions this morning. So, as you can see, the theme our third presentations today is clean energy devices for sustainable future. As you know, one of the problems is the utilization of fossil fuels has really made us researchers to look for the alternative energy. I believe under the current administration of our government is also trying to achieve 23% of new and renewable energy by 2030. And our third speaker today, I think, is the expert in this area because he thinks it day and night, I believe. Right? So before we begin, I would like to read the resume of our third speaker. Despite the fact that his name is not really sound Japanese, he works at the Tokyo Metropolitan University in Tokyo, Japan. Dr. Jacob Mulyana obtained his PhD in chemistry from the University of Melbourne in 2010. He was also the GSPS fellow in the University of Tokyo from 2013 to 2015. He works mainly on the photo-driven water splitting, dye-sensitized soil cell, bio and inorganic chemistry, molecular nanomagnets, and supramolecular chemistry. So without further ado, I'd like to invite please Dr. Mulyana to present his presentations this morning. So the floor is yours.
Thank you, Mr. Chairman. Good morning, everyone. My name is Dan, and my presentation is that. I am now working in Tokyo University in Japan, and I also am part of the Research Center for Hydrogen Energy Based Society, which was newly established in Tokyo Metropolitan University in Japan. But before going into my presentation, I would like to explain a little bit about the historical side of that name. I'd like to have that story. Well, as you can see, that Mulyana is Sundanese. So I am from West Java, and I was born in Cianjur. Yes, I was. So then I settled in Australia back in 2001. So it's been like 17 years. I settled in Australia. That's why there is like a wise word like di mana pun dipijak di situ dijunjung, just like that. So I have to respect the Australian culture. That's why I added that J as a first name. So that's why my first name is now changed a little bit. It's kind of Aussie, but it's not really. Because I'm still Indonesian by skin anyway. And I can still sing what is it? The national anthem. That's right. Yes. So my current focus is on clean energy devices for a sustainable future. That's what I'm focusing on at the moment. But I had a long story of research actually. I started my PhD on the coordination polymers. I'm not sure if you're familiar with a person named Len Lindo in University. I think knows about him. So that's my supervisor in Sydney University. Then I moved to Melbourne University for my PhD. I was working on magnetic materials. Then I moved to James University in Townsville. Richard Keane, you know him as well, was on the pharmaceutical drugs. And after that I switched to the energy devices for hydrogen production from water. Right, so I can't remember, I think it was a few days ago I gave a lecture on the Industry 4.0. If you see this picture, I guess everyone will be aware of the fact that we now live in the age what we call Industry 4.0. Right, everything is digitalized. Everything is about technology, everything is about advanced materials, everything is about, you know, kind of advanced things. So if we take a closer look at the mega trends that we have now, it's all about physical, digital, and biological advancement that we have now. But unfortunately, very few of us actually understand that we live in the earth which is no more comfortable. Professor Chow from Taiwan already explained about this condition, right? If we look at this statistic, for example, the climate change has occurred since the start of the counting of the, you know, when we see there is suddenly an increase in temperature starting maybe about 1960, and that's really dramatic. Up until now, I think back when I was a little boy, when I was born in January, and I was like maybe about 28 to 27 degrees on average, or 30 maybe, but now when last time I went back there and the temperature suddenly rises to about 32, 34 sometimes. It's very, very hot. And I also have a lot of friends in Japan that have also the same feeling. I'm not sure about the UK or about people in Europe. Maybe they also feel the same thing. But that's the fact. The earth that we live in now is a no more a comfortable place to live in, unfortunately, despite the fact that we now live in the age of Industry 4.0. So, what's the cause of that? Everyone knows about the cause of the climate change, which is the carbon dioxide emissions from the burning of the fossil fuels. Professor Chow also had already explained this previously in his talk. The fossil fuels trio, which is the natural gas, the oil, and the coal, is the culprit of the carbon dioxide emission, because unfortunately we rely on the use of these fossil fuels until now. It's probably about 80% of the energy that we use today actually from natural gas, oil, and coal. Right. So you can see here there's a dramatic increase in the carbon dioxide emissions starting from 1950 up until very recently. So that's the culprit. So these are the facts. We have a lot of environmental damages, unfortunately. We also have high demand of energy because of high population, technological advancements, everything is digitized, everything needs energy. So there's high demand of energy. Unfortunately, the fossil fuels diminish really quickly. So we will no longer have fossil fuels in the future. So for example, at the current consumption rates, the world coal reserves could only last for about 120 years. You can imagine that. The oil, the one that we rely on to run cars, trucks, everything like that, will only survive for about 45 years. If my age now is about 40, then 45, at the age of 85, I don't think I can have that kind of, the cars will run under the oil. And the natural gas will only last for about 60 years. So this is worrying, because in the future I don't think we can enjoy the life with the fossil fuels anymore. Right. So so we have a lot of questions now. How can we save the earth then? Right. How can we create a sustainable future for the new generations? So these two questions are kind of the main questions we have now. We have to have that good answer for these questions. So Professor Chow as well has already explained about the options of renewable energy technologies, for example, solar photovoltaics, tidal power, wind power, hydroelectricity, biomass, everything that is categorized as the renewable energy technologies. But what I'm focusing on in Tokyo Metropolitan University is developing hydrogen fuel as the alternative energy, which is very promising to replace the fossil fuels. Right, this is the picture of Japan, how Japan is very serious in terms of developing renewable energy based on hydrogen fuel. Right. I'd like to explain a little bit more on what's happening in Japan in terms of the planning. We are trying, not we, because I'm not Japanese. I cannot speak Japanese. I'm probably the worst foreign workers in Japan because I cannot speak Japanese really bad. So we are trying to build this society called Hydrogen Society in 2020, which is in coming years. What is hydrogen society? Hydrogen society means that everything comes from hydrogen. So the hydrogen fuel is installed in the house and it's connected to the community. So the houses are interconnected. The fuel cells are installed in every house, things like that. So everything comes from hydrogen. The cars, trucks, everything. So that's why hydrogen society. Sometimes people call it hydrogen economy because it builds into the economic values of the fuel. So those who are interested in going to Tokyo for the 2020 Olympics, I'm not sure if you're familiar with the icon. Back in 1962, I think the first Tokyo Olympics, the Shinkansen was the icon for the first Olympics. But now the Tokyo government has the new icon for the 2020 Olympics, which is hydrogen energy. So that's how serious Japan is concentrating on the hydrogen energy development. And if we look at that statistics, for example, that's the future plan that Japan needs to develop new employment opportunities as a result of the advancement in hydrogen technology. So for example, by 2025 to 2030, there will be new employment because of the industry in the hydrogen fuel. already in the market, I suppose, in Japan is, I'm not sure if you're familiar with the Toyota Mirai hydrogen fuel cars, and that's actually based on the fuel cells, and fuel cells on hydrogen fuel, right? So they are really serious in developing, although there are a lot of challenge from America, because they develop also the electric cars from Tesla. So as I told the students last time in my lecture, America and Japan is kind of, just only defining what electric cars are. They are now in competition really hard between America and Japan. America says it's battery, not hydrogen, but Japan says, oh, it's hydrogen. Although both of them are electric, but one uses hydrogen fuel and the other one uses battery. So it's kind of two different things. But both are the same. Both are electric cars, by the way. But only, just defining it is like kind of, competition. And I'm sure in the future there will be a lot of new competition as well. So hydrogen is the research that I'm focusing on in Japan. If you look at the methods or ways to produce hydrogen fuel, there are at least 3 methods that can produce hydrogen fuel. The one that is very common that we have now is from fossil fuels, unfortunately, and also quite the same as the second choice there. And the third one is from renewable energy, which we can get it from water. These two, unfortunately, still produce carbon dioxide, which is not really clean. Although it's majority, although it's the main method that we use now, but it produces at the same time carbon dioxide emission, which is not what we want. So we need to think about alternative ways to achieve hydrogen from something cleaner. Right? One way is to get hydrogen from water. How do we do that? Is by we are all chemists. I think some of us maybe from other subjects, but water produces oxygen and hydrogen using electrolysis method. Right? That's the method that we can use, and my research is very specific because what I aim is producing hydrogen from water using light energy. So that's my aim. It's not. It doesn't use any electrical current. It doesn't use any other external trigger. It's only just by light energy. So that's my aim. It's really difficult to achieve because of the energy demanding process. So now it comes to the very technical terms, which I'm sure everyone will get bored, but I hope that it's not. So the device that I developed in my laboratory is photo-driven water splitting. Right. The specific device that I developed is dye-sensitized photoelectrochemical cells, or DSPEC. So if we have the water as the water feeding, then it can go to oxygen when we use water oxidation catalyst, or WOC. But we need another component, which is the dye, to absorb the light energy. And the dye can be attached to an appropriate semiconductor, for example, titanium dioxide semiconductor. And attached to that is FTO conductive glass, because we need to have everything connected in terms of the electricity. Right, and if the dye absorbs the photon energy, that dye can be excited into the excited state. That excited state dye can inject the electron to the conduction band of the titanium semiconductor. And that electron moves towards the external circuit to reach the platinum side, where the proton that comes from this process can be reduced to hydrogen gas. So that electron is extracted from the oxidation process because of the WOC activation by the dye. So there is an electron relay from this to WOC to the dye to the conduction band of titanium, and then going through the external circuit and reaching platinum side as the counter electrode, where we have the hydrogen fuel output. So that's how we can get the hydrogen through the light energy. It's like an indirect process because we need kind of cascade electron transfer from the water oxidation catalysis to the dye and to the semiconductor. So why is this technique promising? Because it's cheap. Titanium oxide is not that expensive, and it also allows us to modify the system through the synthetic designs. We can design a lot of water oxidation catalysis molecule. We can also design dye molecules, the one that we want. So the benefits are they are cheap, and also they allow us to modify through the synthetic designs. Right, but we are facing a lot of challenges. That's why I'm trying to face those challenges. The first challenge is that the photocurrent decays very rapidly because of the fast charge recombination. But you already asked the question last time to the last presenter. And also the materials desorption from titanium dioxide, that's the second problem. So in terms of the photocurrent, we have to face that challenge. The second challenge that I would like to address in my research is that not all dyes can absorb a wide range of sunlight spectrum. It's very limited. It's only probably the common dyes can only absorb up to the visible region, up to there. But very limited dyes can absorb up to the near-infrared region. So my challenge is to build or to synthesize the dyes which can absorb visible up to the near-infrared region. At the same time, that dye can induce the water splitting process in the photoanode compartments. So what I tried to develop is what we call panchromatic DSPEC. It's the one that can absorb a wide sunlight spectrum, which we call panchromatic. And the one that is robust, the one that can survive under constant light irradiation. And also the one that is efficient, which means that it can convert photon energy to current or to electricity very efficiently. Okay, so first of all, I'd like to explain about our finding on the panchromatic DSPEC. As I said before, what I designed is I need to get the dye. I need to get the dye which can absorb the wide sunlight spectrum. And the dye that I was interested in, and another collaboration with another professor in the university, is this body B dye, organic body B dye, which we can see the IPC spectrum of the body B only, and with the body B plus the WOC, we can see it absorbs wide. So the IPC goes to the near-infrared region. So which means that this system is panchromatic. How do we know that the two are in coexisting, because we see the cyclic photomograms of the DSPEZ. That is the one, the dye only, the green one. The blue one is the WOC, and the red one is the combination between WOC and the dye. So, because of the IPCE, which shows the panchromaticity, then we can prove that this system is panchromatic. So then we move to the analysis of the water splitting performance. Keep going that way. So both in pH 5.9 and 7.2, we can see that indeed we have water splitting process happening in the system in exactly 1:2 ratio of oxygen and hydrogen. So it's kind of true water splitting, although the Faraday efficiency of oxygen formation is not that high, but we can see there's an increase in Faraday efficiency from about 44.5 to about 76.4 in pH 7.2. So you can also see the photocurrents, for example, in pH 7.2. That's the body B only, the dye only, and this is the combination between the body B and the WOC, which increases significantly, which leads to the formation of water splitting process. So how do we check the electron relay or the cascade electron transfer happening? It's possible because according to the CV data, the WOC catalysis of water oxidations occurs at about 0.9 volts, and the electron can be extracted because the hormone energy of the D1 of the dye is actually about 1.06, and the excited state energy of the dye is about -7.2, which is more minus than the conduction of titanium nanoparticle, so that the electron can be transferred to the conduction band of titanium. So in terms of the energy diagram, that process is possible. So that's why we see that kind of process happening. Right, so that's the panchromatic water splitting. The second thing that I'd like to explain to everyone here is the robust DSPEZs. The approach that I was choosing was the designed using hydrophobic or hydrophobicity approach. Why do I choose that kind of approach? Because I think everyone knows about hydrophobicity. When we put a hydrophobic functionality into a chemical compound, then that compound will dislike water. So consequently, it doesn't like water, so it will stay in the nanoparticle longer than the one without the hydrophobic functionality. So that's my assumption. And according to the previous publication about this is what called RuBB, the most common dye used in dye-sensitized solar cells, also in the dye-sensitized photoelectrochemical cells, DSPEZ. The weakness of this dye is that it dissolves from the titanium oxide nanoparticle surface above pH 6. So that's why I developed something new. I tried to have that kind of longer alkyl chain, which is the nonal chain, also jet-butyl chain, just to replace or to modify the hydrophobicity of the dye. So let's see what happened to that. First of all, the electrochemistry of the dye. The comparison is shown here. The red one belongs to the one with the normal group, which we can see here. That's the redox potential increases to about 1.47 fold, which is really high. But the one that is the parent one only stays about 1.3 fold. Only from that data, we can see that the introduction of the non-null group actually is better because it gives higher oxidation potential, which is really good in terms of the water splitting process. And what about the stability data? At pH 5.8, this is the one that we check after soaking. We check the absorbance of the dye in the solution. Right. So the red one, you can see there's only very few detaches from the surface because it stays pretty strong on the surface of the titanium oxide in both pHs, in both pH solutions. So from that data, we can conclude that the run BP, I call it run BP, shows higher oxidation potential first of all, and the second one is it less dissolves from titanium oxide surface. Right, and we were also interested in analyzing the performance of the hydrogen production of the dye in the DSPEC device. So pH 5.9, pH 8.1, you can see here from the photocurrent performance, run BP is much higher than the root BP. You can see that blue one is root BP and the red one is run BP. And you can also see that the hydrogen production is more for the run BP in comparison with the root BP, with higher Faraday efficiency as well. As you can see here, that is the solution of the root BP after soaking, which clearly detaches from the titanium because of the coloration of the solution. But that one stays clear, which means there's no dye detaches from the surface. Right. But I was also interested into going into the deeper part of the process of the phenomenon, and I asked the student to analyze or to have more detailed using the methyl group, the butyl group, and also the nonal group in the dye-only DSPEC. This is dye-only DSPEC. It's not really common to put only the dye on it because we normally need catalyst, but I asked the student just use the dye first and see what happens. Right, because we only want to sort of scan or sort of compare the P1, P2, P3, P4 in terms of the introduction, in terms of the going higher from without adding any substituent, to have the methyl and to have the terbutyl and nonal. Right. The photocurrents, as you can see here, that's again in the dye-only device, run BP, which is the nonal group, has the highest photocurrent, followed by the green one, which is the terbutyl, and the P2, which is methyl, and P1, which is nothing inside the ancillary ligand. So the performance rank in the dye-only DSPEC is P4, followed by P3, followed by P2, and P1. It's also consistent with the IPCE spectrum. You can see that's the IPCE spectrum. That's the highest one, and the one without anything is the lowest one. Right. Okay. And I was also interested in analyzing the detailed using the the titanium oxide and also the solution. Right. So because we work on the die-only system or die-only DSPEC, then we need to understand this kind of phenomena. Right. And we also need to understand what's the electron injection capability of the die. So we also need to check what's the excited state potential of the dies, and we need to compare them. So all dies have close excited state potential, which means that they have similar capacity to inject electrons to titanium oxide. Right. P2 and P3 have more negative ground state potential, which means there is an electron donating effect. Right. P4. Why does P4 shows the highest performance? Because when we check the excited state lifetime in solution, that's actually the highest one, as you can see here. It's about 692. And when we compare the excited state lifetime in solution and in titanium dioxide, we can see here that the decrease in the excited state lifetime is the most extreme in P4, which means that the electron injection to the titanium dioxide nanoparticle is more effective in P4 compared to the other dyes because of this reason. So there was a very interesting phenomenon after analyzing the die-only device. We were interested in the next method, which has the sacrificial agent onto the system. The sacrificial agent that we tried was EDTA. Right. It was really interesting because the performance is kind of the other way. It's not the same as the die-only, but it's like the other way. Completely the opposite. That's why it's really interesting. No one has published this before, and that's why we were interested in going deeper into that kind of phenomena. So the photocurrent, for example, the one that has the highest photocurrent in the sacrificial, what I call it SADSPC, is P1, followed by P2, and then P4 is the poorest one, unfortunately. Right. Although the photocurrent, you can see here, there's a lot of increase in terms of the photocurrent from about microampere to about milliampere in sacrificial agent, which means that this electron relay occurs in the system, so that ruthenium-3 shuttles back to ruthenium-2 because of the oxidation of the EDTA to EDTA class. So the performance rank from the photocurrent decay is P2, followed by P1, followed by P3 and P4. You can also check the hydrogen production over time. For example, after about 5 hours, you can see here that the top one is actually P2, followed by P1, P3 and P4. It's not going to take much. Right. All right. So I'd like to continue into the reasons why P2 is the top one. It's because of the reorganization energy factor. Right. So the one that has lowest reorganization energy is actually P2. So that's why, in terms of the shuttle state from ruthenium-3 to ruthenium-2, we need to consider the reorganization energy from 3 to 2 because of the presence of EDTA. And when we check the reorganization energy, the lowest one is actually P2 and the highest one is P4. So that's why we clarify in the end that because of the reorganized energy which is higher in P2, that's why the performance of P2 is the top one. I guess I have to skip this. The diet disruption studies clearly shows that P4 is the one that actually less dissolved from the system. I'm not sure if you're interested in the metal oxide solution interface because this one is taking more time. But let me just explain a little bit on this one. I was also doing the metal oxide solution interface approach, which uses only the metal complex put in solution on IT or nanoparticle. And I was able to demonstrate that the dinuclear complex, for example, is more active than the mononuclear complex because of the scaffolding effect, as you can see from the photocurrent data. And also from a lot of experimental supports. I think because of the limitation of the time, I need to kind of go into the conclusion. So, panchromatic, robust and efficient devices for hydrogen fuel production from water. I hope that I have explained to everybody that I'm going towards the sustainable life in the future. And I have made a lot of efforts into the panchromatic dye-sensitized photoelectrochemical water splitting and the subtle structural change in the ancillary ligand of the metal complex can lead to an intriguing phenomenon of the electron injection capability as well as the reorganization energy and the dissorption rate. I don't think I have to explain that one because it was skipped. Right, so I have to thank the collaborators. So my work is supported by so many collaborators, including within the university and also from University of Tokyo. These are my students. He is from Indonesia, he's also from Indonesia. He's from Japan, he's working now on a master project. Also, the connection with Australia still. Leon Spicia already passed away, but the research is still going to Monash University. Also with the company in Japan, Nippon Kayaku, it's quite a big company. And also with ASIS in Australia. If everyone wants to visit Tokyo, you're more than welcome. This is the campus of Tokyo Metropolitan University in west of Tokyo in Hachioji. Just very far away from Tokyo Center, but especially in cherry blossom time, it's very beautiful. Thank you very much.
Thank you so much, Professor Mulyana. I noticed that your hobby is running, right? So it's pretty much similar to mine. 7. I like, instead of running in the track, I like to running late and running away from my responsibilities. Right.
My last achievement was 10 kilometers.
All right. So a few key points on the top that the hydrogen society in Japan is really it's a big thing, and one way to achieve that is through water splitting technology that Professor Mulyana has really developing on the panchromatic, the SPEC, using ruthenium complex and organic dyes. Right. So I would like to invite audience for questions. Anybody? Yes.
Yes. Thank you for the opportunity. My name is Asman Komik from Department of Chemistry, Universitas Indonesia. I would like to ask some questions about your presentation. The first question is about the challenges that you've explained before about the fast charge recombination. I would like to ask more in depth about this. And the second question, in your material using the titanium dioxide, is it in nanoscale or is it in nanoscale, the titanium oxide? And what do you think about the hydrogen production will be applicable in Indonesia? Is it possible? And what about your vision in Indonesia to change their consumption in hydrogen fuels beside from the coal or fossil fuels? Thank you.
Okay, I think the first question is about the chart recombination. Let me just explain with the diagram. I think Professor Chow knows more about this than me. Maybe you can explain about that. Well, if, for example, if the semiconductor absorbs light energy, right? The electron from the valence band moves to the conduction band, right? But before the electron can move to for example, FTO or something else in the other junction, that electron from the conduction band moves back to the valence band. That's why that rate sometimes is really fast. So we cannot handle that situation. So that's why the good strategy is just to prevent that recombination from happening by any means. Either adding this sacrificial agent or catalyst or something, just to trap that hole before the electron recombines with the hole. So that's a technique. So for example, here I have ruthenium 2 species, which oxidizes to ruthenium 3. That process uses the hole. So before that electron recombines with the hole is already used by something else, something like that. So that prevents the electron recombination. So that's a technique, and it's quite similar to, I'm not sure, maybe yours, Professor Chow's system is also the same. Is that the answer to your question? I think so. What's your second question? I forgot.
Whether the titanium dioxide was the nanoparticle.
Oh, it is nanoparticle, yes. It's nanoparticle. Yeah. But there are a lot of, phase, maybe rutile or anatase. We have a lot of options that we can use. Yeah. So the third question was about hydrogen energy in Indonesia, right? Yeah. It's difficult to answer because it depends on the country itself. Even in Japan, the hydrogen society that we try to build in 2020 is still underway, and we still need a lot of infrastructure to be built. And our aim is just not the whole Japan, but only the metropolitan government. Tokyo has 21 wards. It's only around that area. So the society that we try to build is around that 21 districts, not excluding Yokohama, excluding Saitama, excluding Chiba. So only Tokyo. So you can imagine Japan, who is developed, that still doesn't have the capacity to build for the whole country. So that's why it's still ongoing. Hydrogen fuel, it's not always available. The Japan government is trying to build many hydrogen stations, but as I said, we have a problem. The main source of hydrogen fuel, it comes from fossil fuels, steam reforming, and things like that, which still produces carbon dioxide emission. That's the drawback. So my research is focused on something cleaner, which is also a problem. Well, it's very difficult because it's the efficiency that I've shown you in my presentation. It's probably around 0.5 or 1% efficiency. It's very, very just nothing. So it's still like small kind of beginning of the research. So that's if you understand the degree of difficulty. Well, when I signed up for this research, I knew that it's going to be very difficult, and I knew that it's going to be challenging, and I knew that there will be very few interested in my topic, and you know, it's true. So that's why if we think about how to build hydrogen energy in Indonesia and how to build an infrastructure, maybe we can study from Japan first of all, or Australia, or maybe Korea. I think Korea has started to build that kind of infrastructure already. So try to study from other countries and then how we can apply in this country.
My name is Prof. I'm So I think already answered. So I was going to ask about why I think the sacrificial agent is the EDTA. Why is it a sacrificial agent?
So your question is why EDTA? Why I use EDTA?
Why do you call it sacrificial?
Sacrificial agent because it eventually will be used up, will be gone. So it's not repeated, it's not recycled. If, for example, this one can be considered also sacrificial because we start from ruthenium 2 and we end up with ruthenium 3. If we can recycle 3 to 2 again, which means it's not sacrificial, it's recycled. But if it's used up, it's like gone and eventually, that's sacrificial. All right.
Yes.
Thank you.
Professor Mulyana, I'm Agustus from FMIPA. Actually, it's very interesting. I also did some photocatalysis work back in the UK when I was doing my question is, please don't take it like it's a little bit because I want to question what is the motivation of use the titanium oxide as the intermediate layer between your photoanode and the material, because the balance band of the titanium oxide is very weak. So depending on what kind of light you use, it's actually the one that could probably oscillate the vibration because it could be some kind of X-ray UV light that is inside the light from the titanium oxide. And then after that, the other one is I think your dye is probably strong because when you see the data from without the sacrificial electron and with sacrificial the difference is very, very much. 200 microns to 6 milliamp. So basically the hole is basically just trapped inside the dye or maybe just inside the catalyst. And it's not really transferred into the water to oxidation. And then probably you should, I'm not very sure that the carrier lifetime is the electron lifetime or is it the lifetime? One of your slides you showed that there is like the decrease in the carrier lifetime from hundreds of nanoseconds. So you can see that. Yeah, this one.
The lifetime.
So it's a compilation of questions. So yeah.
Okay, so the titanium oxide, it's true. Well, the band gap is quite high, like 3.2 electron volt, and it's not really, well, it's still considered the good semiconductor for this type of dye-sensitized photoelectrochemical cells. It's true that the UV, absorption can damage the dye. That's why my system cuts the UV lights. So we have the UV filter. So the hole doesn't actually, the electron from the platinum is made from titanium. It doesn't go into the conduction band of the titanium because we prevent that because the light that we use is visible, so it doesn't absorb much in the visible region. Right. So the one that we try to target is the dye absorption, the light absorption of the dye. Okay? So that's the titanium dioxide.
I think there's not really an efficient whole transfer.
Okay, yes, that's right. Yes, you're true. You're right. The study here is the comparison between dye only and sacrificial sacrificial agent is to analyze the details of the phenomenon of the change in the alkyl substituents. That's the phenomenon that we want to study. Is there any influence of that substituents to the activity? And we found exactly what we want. In the dye-only system, the order is P4, P2, P3, P2, P1. With sacrificial agent is the other way. So there are a lot of parameters, so it's not simple to explain the phenomenon of the dye-sensitized photoelectrochemical cells. It's not a simple thing, in fact, because even when we try to have that subtle change in the substitution of the alkyl ligand, it changes everything, many things. So we can see it from the excited state lifetimes, from the electron injection ability, as well as from the reorganization energy, which is completely different thing. So that's the study that we try to get. It's not exactly, the performance. The performance is very poor. Especially when we talk about the ionic system, it's very poor. But the sacrificial agent, it might have a lot of, good results. Yes.
Going forward, do you think instead of using titanium oxide, is it better to do a tandem where you have photocathode and then the combination between cathode and
True.
photocell?
Yes. We try to. In the future, we try to have that. Instead of using maybe platinum, we use also photocathode just to reduce proton to hydrogen using photocathode. So everything goes cheaper. Titanium oxide on the photoanode and the other one for the photocathode. So that's one way. And I'm also now developing bismuth vanadate semiconductor, which is also cheaper and more efficient. So there are quite a lot of new products.
Thank you.
Thanks.
Right, thank you. A very interesting topic indeed. But unfortunately, the time is up. So let's give Professor Mulyana a big round of applause once again.
Thank you for Professor Mulyana for your intriguing presentation. And also we have Dr. Dede Johanna from Research and Public Engagement Division representative to give his regards and the souvenir towards the Professor Mulyana. Ladies and gentlemen, as the end of the plenary just now, we would like to invite the audience to enjoy the reserved lunch before continuing to the parallel session at 1 p.m. Please enjoy the reserved lunch in the front of the room. And please bring your belongings, and the information about parallel room session is available on the registration table. Thank you.